good evening to all of you. Good evening to all of you. So today mainly we'll focus on adjacency algebra. That is, if A is a adjacency matrix of a graph, then set of all polynomials in A is the adjacency algebra. That is a vector space as well as a ring structure, and so it has very nice properties that we'll explore today. So, but before that, I'll state some results. We already discussed, Rajesh Kanan sir already maybe discussed with you and other faculty. Okay, so I may skip proofs, but let us understand the statements because these are needed because we are working with symmetric matrices. They are diagonalizable. Okay, so I put those statements and proofs here. Already discussed maybe, but you have one more source now. We can go through these slides, and anyhow I'm sharing everyday slides with you. You can go through it. Okay, so a matrix is diagonalizable. So diagonalizable, you know, it is similar to a diagonal matrix. Diagonalizable if and only if it has an linearly independent eigenvectors, right? Yeah. Okay. So the proof is very simple. Okay, if it has linearly independent eigenvectors, then I can form a matrix. I need to show it is the diagonalizable. Then I can construct a matrix with those as column vectors. Then that will work. That is our P. Okay, PA P inverse equal to diagonal. So that is easy. Next, if it is a converse part is that if it diagonalizable, then I can take those P as column vectors and will work. So both the sides is not tough. Okay, diagonalizable if and only if it has linearly independent eigenvectors. Okay, so that is the proof of here. So that is the first result. And this I discussed in the first day, right? First class. If A is diagonalizable, then rank of A equal to number of eigenvalues of A, non-zero eigenvalues of A. Okay, because it is similar to a diagonal matrix. Diagonal matrix rank is same as the number of non-zero diagonal elements, but that is exactly the eigenvalue. So that is the connection, right? So proof is given here. So that is spectral theorem of symmetric matrices that I've discussed already. I'm giving a lemmas. So finally, that result can be proved. If A is a symmetric matrix, then eigenvalues corresponding to distinct eigenvalues are orthogonal. Eigenvectors corresponding to distinct eigenvalues are orthogonal. Further proof is given. Eigenvalues of a real symmetric matrix are real number. That is also easy to see. Okay. Then if U is invariant under A, then U perp also invariant under A for real symmetric matrix. If U is invariant, U perp is also invariant. Okay. Yeah. So before other people join, just I'm recalling what is other faculty discussed with you. Okay. So later you can check proofs here also available at one place. Okay. If U is a non-zero invariant subspace of Rn, then U contains a real eigenvector of A. Because zero space is also just zero vector. That is itself is a subspace that is invariant also, but it is not eigenvector. It does not contain eigenvector, right? Eigenvector is always a non-zero vector. Okay. Yeah. So real symmetric matrix, invariant subspace, any non-zero invariant subspace contains an eigenvector. With that, we'll prove the main result. A is a real n by n matrix. Then Rn has orthogonal basis consisting of eigenvectors of A. Okay. So this is the result we need. Okay. So yeah, this we are already using in other courses. Okay. So that is the thing. So now this is a starting point today. So by this time, I hope all of you are already joined, right? Yeah. So you want to ask any questions? Do you want to ask any questions? You can ask. Okay. So I'll proceed now. Yeah. So this is the result. This is also discussed, but very important. So I'm just recalling and try to see its proof also. Yeah. So starting point today. If this is very useful for us throughout. If let X be a graph with the adjacency matrix A, then every for every positive integer k, a power k, ijth entry will be equal to the number of walks of length k from vertex vi to vj. Okay. Is anyone know the proof? How to prove it? Can you take guess? Is anyone of you know how to prove this? Generally, here what is that we need to prove for every positive integer k. So then usually what is the technique we will use? Something we want to prove for all positive integers. What is the general proof
By
technique?
induction.
By induction. So we'll follow by induction. For k equal to 1, it is easy, na? K equal to 1 means the adjacency matrix itself. What are the entries of the adjacency matrix? Zeros and ones. Okay. One meaning what? There is a walk of length 1. Actually, there is an edge between the vertices, right? When we put 1 in the adjacency matrix, there is a walk of length 1 from I to j. Okay. Otherwise, it is 0. There are no walks, right? So there is no walk of length 1. So a power 1 is exactly that number of walks of length 1 from I to j. So we'll assume the result is for k, then we'll prove for k plus 1. Okay. So that is the proof, right? Okay. So assume it is true for L, then you will take a power L plus 1. And you know matrix multiplication ijth entry, you will multiply row with the column h equal to 1 to n, al, I, ih, a, ij. In AL, a power L, IH entry is number of walks of length L from I to H. And there is one more one, then I'll get a path of length L plus 1 from I to J, right? So that is actually the proof, not tough, right? Yeah. So hope it is comfortable. Can you take this? We are using it every day, right? Can you take guess, please? Yeah. Okay. Right. Today I'll go a little slow. In the last class, you told that. Yeah. So, okay. Thank you. So we'll move forward. Yeah. Okay. Yeah. So the one of the question you asked is that what applications of adjacency algebra that now we are doing. So now we will enjoy this part. Okay. Okay. So first object in that direction is this. Okay. If X is a connected simple graph on n vertices, connected graph, and D is a diameter. Since it is connected graph, it has a diameter, right? Then we need to show that dimension of the adjacency algebra is lies in between D plus 1 and n. D is the diameter. Is the statement clear? What is the A of X? Is adjacency algebra of X. What is adjacency algebra? That is set of all polynomials in A, right? So collect take any polynomials in C and substitute A, we'll get matrices, that collection. Okay. And is any one of you recall that what is the dimension of A of X? Last class may discuss yesterday. Is anyone can recall? Dimension of the adjacency algebra. Can someone tick? So we saw that is C of A, that is isomorphic to C of X quotienting minimal polynomial of A, right? Dimension of A of X is exactly the degree of the minimal polynomial or number of distinct eigenvalues of A. That is the thing. Okay, am I clear at least now? Dimension of A of X is degree of the minimal polynomial of A or number of distinct eigenvalues of A. That is the dimension. Now we are saying that the degree of the minimal polynomial is at least D plus 1 and at most n. Or otherwise, we are telling number of distinct eigenvalues of A. These are the bounds for the number of distinct eigenvalues of A. A is the adjacency matrix of the graph. Okay. So that is the problem. Okay. Yeah. One thing is easy, right? Less than or equal to n easy to see. Is anyone comment? Number of eigenvalues, distinct eigenvalues less than or equal to n. That is easy, right? Because matrix size itself is n. If A is a matrix of size n, then it has at most n eigenvalues. That is easy. So the question is that how do you show that number of distinct eigenvalues is D plus 1 or more. Okay. What is D? D is the diameter. That is the problem. Okay. So clear? Statement is clear? Can you tick yes, please? Now, is it everything fine? Somebody can tick, please. Just is a statement okay. Dimension of A of x means number of distinct eigenvalues. That is also equal to the degree of the minimal polynomial of A. Okay, thank you. Yeah. So how to prove it? Is anyone has some clue? Does anyone want to comment before I show the proof? Okay, no issue. You can somebody answer this. If the diameter of the graph is equal to D, what is the meaning? Diameter of some graph is equal to D. What is the meaning? Your voice, you can mute it. Divya, can you mute, please? Yeah, thank you. Is somebody else? Okay, she's trying to answer, but someone else can tell. Diameter equal to, what is the meaning of diameter is D? Okay, so I think Divya may be saying this part only. There is an edge. Sorry, there are two vertices. The distance between them is D, and that is the largest distance, right? In that entire graph, may. So that is the largest path in the graph. That is one of the largest path in the graph. There are two vertices. The distance between them is D, and that is the maximum possible distance in the graph between any two vertices. Okay, that means that. So what is that A square A cube they are giving? They are giving number of paths of length k from I to j. Now, if there are two vertices I and j, if the distance between them is say d, then so let us say d equal to say 5. Okay, d equal to 5. Diameter between I and j is 5. Then what is A square coefficient? In A square, what is ijth coefficient? Somebody can point out that. The distance between I and j is 5. Then what is the quotient of ijth coefficient element, ijth element in the matrix A square? In A square, ijth entry is number of walks of length 2 from I to j, right? Now I am telling I to j the distance is 5. Now what is the value of ijth entry in A square? Can someone unmute and say?
0.
0, right? Yeah, it is 0, right? Yeah. So A square entry, ijth entry 0, A cube ijth entry 0, A power 4 ijth entry 0, right? A power 5, suddenly it becomes some number, right? And also there is a path from I to j of length 5, meaning, okay? So there is a path of length 4 from I to some vertex, right? There is a path of length 3 from I to that some vertex, right? And that entry become 1 when it is become 4, 3, like that. Okay. What I want to say, so happens is that the a square a cube. Okay. So I'm a square a power. These are all matrices. Okay. These are linearly independent. A square a power d. Why they are linearly independent, right? So a power d pay only in a power d, but only at d ijth entry become 1. Okay. Only at d power 1, one entry from I to one vertex is 1. Before that, it is 0, right? So like that it happens. So that's because of that, it is easy to see that these are linearly independent. Is it clear? Is it tough, or you need more explanation? It is beautiful, right? Between I and j, the distance is d. Here I told x and y. Okay, you can see here. Okay, otherwise, okay. Between x and y, distance is d. Okay, so then automatically W naught and WD, the distance between W naught and W1 is 1. W d minus 1, it is a d minus 1, right? So a power d minus 1 only, that entry become 1. Before that it is 0. Because there is no even path how walk will come, right? Yeah, okay. Any questions? Can I proceed? Can you take guess if you are clear or not clear? What I'm simply saying is that a square up to a power d, they are purely linearly independent. That means I cannot express a power d as a linear combination of the previous thing. That means degree of the minimal polynomial is at least d plus 1. None of these I expressed as, they are linearly independent. Na? Independent means I cannot express one as a linear combination of others. That means the minimal polynomial degree is at least d plus 1. Okay, am I clear or not clear? So if you are clear, please tick yes. I'll proceed. Okay. Hope so everyone have clear about and assuming that and moving forward. But before that, again, try to recall what is that we are done. Dimension of the adjacency algebra. Is connecting with the diameter of the graph, right? Yeah. So let us see that. Okay. Yeah. This is a interesting thing, right? A connected simple graph with the diameter d has at least d plus 1 distinct eigenvalues. That is clear, right? So proof is also not required. I told dimension of AF is exactly equal to the number of distinct eigenvalues. So it is at least d plus 1. Okay. Yeah. Now look at this. If all eigenvalues of a simple graph are equal, then what happens? If all eigenvalues of a simple graph are equal, right, then what happens? All eigenvalues are equal means number of distinct eigenvalues is only 1, right? And we know that it has at least d plus 1 distinct eigenvalues, but there is only one eigenvalue. That means diameter is how much? 0. Diameter is 0 means what? It's null graph, empty graph, whatever you call, right? Okay. So if a graph has only one eigenvalue, then that has to be null graph. If it is a null graph, then automatical eigenvalue is 0, right? So it is if and only if condition. Okay. If a graph has only one eigenvalue, then that has to be empty graph only. Empty graph or null graph, whatever you are using, that is the thing. Means isolated vertices. Am I clear about this? Can you tick yes if you are clear about? So we are characterizing. Very beautiful, right? If only one eigenvalue, no, only one distinct eigenvalue, then it is null graph only. Done, complete. Okay. We are able to characterize the graphs with eigenvalues now. One graph at least. Now let us see. So for example, above result need not be true for directed graphs. We are talking about, okay. For example, if you take a graph like this, okay. 1 map to 2, 2 map to 3. Then what is its adjacency matrix? 1 to 2, there is an edge. So 2 to 3, there is an edge entry. So this matrix, can somebody see? It is a nilpotent matrix, right? All its eigenvalues are 0, right? But still the graph is not a null graph, okay? Directed graphs, thoda sa just careful about, okay? Whatever we are talking about, undirected graphs. But few results may be true for directed also. Yeah, okay. So beautiful result is this. A path graph and n vertices has n distinct eigenvalues. How do you prove this? Somebody can comment now. That will be nice. If you say that will be nice, I'll get some motivation. A path graph and n vertices has n distinct. Yeah. Ah, yeah. Right, right. Yeah, correct. So path graph diameter is d, right? Diameter is n minus 1. Diameter of path graph is n minus 1. That is the largest diameter it has, right? And out of all graphs with n vertices, path has a diameter n minus 1, right? then automatically, so diameter is n minus 1. Number of distinct eigenvalues are at least d plus 1 and less than or equal to n. So exactly n. So path graph have all eigenvalues of path graph are distinct. Okay, that is one thing. But converse need not be true. In fact, there is a result that there is a every almost probabilistically. So almost you take any graph arbitrarily, it has n distinct eigenvalues. Okay. Yeah. Okay. So let X be a connected graph, then it has exactly two distinct eigenvalues. Okay. If one is a complete graph, are you able to see that? Beauty, right? It has exactly two eigenvalues, and here I told it is connected also. Connected. If X is connected graph and it has exactly two eigenvalues, two distinct eigenvalues, then the graph is complete graph. It is if and only if condition. You know, complete graph has only two distinct eigenvalues, n minus 1 and minus 1. That you already know. Now we are telling converse also. Do this. Right? Is anyone want to comment other than Divya? I think Preeti can try. If it has two distinct eigenvalues, then what you can say about the diameter?
Diameter 1.
Diameter 1. What is the graph whose diameter is 1?
Complete graph.
Complete graph only. Kel Katham, right? Yeah.
Yes.
Yeah. Okay. So that is that. Okay. So complete graph have exactly two distinct if and only if condition. So complete graph are the only graph have exactly two distinct eigenvalues. Okay. But once it is connected, disconnect also not a problem, right? If X is now one more problem. If X is a graph with exactly two distinct eigenvalues, here the definition I am not assuming connected graph. Then it has to be regular. It's a beauty. Okay. It is only two distinct eigenvalues, then it has to be regular graph. That we'll see now. Okay. If it is connected, then we already know it is a complete graph, so automatically regular. And n minus 1 regular. Right? Yeah. So somebody can try. If it has exactly two distinct eigenvalues. Okay. Okay, so let us see. If X has two distinct eigenvalues, then dimension of A of X equal to, correct? Dimension of Edson's algebra equal to the number of distinct eigenvalues. So dimension of A of X equal to 2. Then what is the basis? You know, what are the elements in the adjacency algebra? I, A square and so on. All the powers, all the polynomials. In particular, I, A square, they are also part of it. Now, I and A are already forming a basis. That means that A square is expressed as a linear combination of these two, right? Yeah, A square is equal to A into I plus BA. So can you say something now? A square equal to A into I. What is the diagonal entries in A square? Right? Diagonal entries are exactly the degrees of the vertices, right? In A square. Number of arcs of length 2. How do you get arcs of length 2? So you are at a vertex. You go and again come back. How many edges are there? That many times you go and come back, right? So that is exactly the degree of the vertex. Now you see that that is independent of the vertex. That is A, right? So A square ith entry is A for all I. So that means that it is a regular graph. Degree of every vertex is A. Okay. Yeah. Hope it is clear. Can you take guess if you are clear with? Good. Thank you. Okay. So are you able to see that two distinct eigenvalues if and only if X is actually disjoint union of the complete graphs only with the same number of vertices. Okay. Yeah.
So you told earlier two distinct eigenvalues and diameter 1.
That is when it is connected. See,
Okay.
sometimes graph has two distinct eigenvalues, it may not be connected. For example, K2, K2, K2 you take, right?
Okay, sir.
Yeah. So in that case, eigenvalues are 1 and minus 1 only. K2 के लिए eigenvalues are, but So that is a disconnected K2s. So K2, 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 I take 5 times. Then I still eigenvalues of that graph is 1 minus 1 only, but 1 5 times minus 1 5 times. But
But disconnected, we cannot talk about diameter.
diameter we cannot talk about. Na? Diameter is that distance. First we
Okay,
need
but
to
dimension where you are talking things.
diameter. Yeah, correct. Dimension we can, but diameter we cannot have, right? Yeah.
Yes,
Okay.
yes.
Yeah. Okay. Thank you. Yeah. Thanks for asking. Yeah, that is good. So now the question is that how to check a given graph is connected or not. For this, adjacency algebra is not required, but let us see. How do you check a given graph is connected or not? By using our matrix theory. The goal of this workshop or short-term course is that graphs, matrices, and applications, right? How matrix theory will be helpful, and also sometimes how graphs will helpful to linear algebra. Always not using the linear algebra and studying properties. We have an equitable partition. Equitable partition is a good help to the linear algebra also, right? And of course, maximum times we'll use linear algebra to study graphs, but sometimes we'll have reverse direction also. Okay, yeah, because recently groups and graphs, groups and rings, people are working. So ring theory, by using a ring, we'll construct a graphs and we'll study properties. We can visualize the ring structure and group structure very nicely, and you can tell about the groups and rings also, right? Yeah. So in fact, so in particular, what I'm going to need this class and next class, right? You do not believe that the concept of this distance regular graphs, they are very, very useful to classify the simple groups. Simple groups, right? They are building blocks of entire group theory. So actually many sporadic groups, they actually constructed because of the graphs only. They are automorphism groups of the graphs. Okay, so we'll go back, we'll understand that in the next lecture if time permits. Get back to this. How do you check a given graph is connected or not?
If
Any
adjacency matrix is irreducible, then connected.
okay. Yeah, that is one thing.
If and only if condition.
Yeah, okay. So how do you check a given matrix is reducible or not? Okay, good. That is a nice point. Irreducibility, yeah, but that is one good point. But
The
I'm
directly path.
yeah. Now I'm taking, yes, you are correct. That is what I'm doing. See, an algorithm. How the computer will tell if I give a graph. Giving a graph to a computer means what? You are giving the adjacency matrix, right? Then I'm telling that it is connected. If I plus a whole power n minus 1 is positive. Okay, if X is a connected graph with n vertices, if A is a adjacency matrix, then I'm telling that if it is a connected, then if it is connected, then it is asking reverse now. Connected, then what is happening? Then I'll ask converse also. Okay. If it is connected, then I plus A, I identity matrix plus A whole power n minus 1 is positive. Can somebody point out why it is positive before seeing the proof? Can you think about? What is I plus A whole power n minus 1, right? Okay, even forget about binomial expansion. What do you say about I plus A square up to A power n minus 1? I plus A square up to A power n minus 1. You are adding all of them. First thing you know that A is a non-negative matrix. Entries are zeros or ones, right? In A square also will not get negative entries, right? Then I plus A square and so on, A power n minus 1. If you add all of them, A square and all, then you are telling that every entry is positive. Why? Right? That is the thing. You know that in A square, what is ijth entry? Number of walks of length 2 from I to j. Okay. So if it is connected, it has some diameter. You know diameter is at most n minus 1, right? With n vertices. Okay. So that means that you take any two vertices, there is a path. Okay. Then that means, so then that power you do, then automatically that entry is positive, right? Beautiful, right? Hope very clear. Okay, what I'm saying is that so a square, a cube up to a power an minus 1. Yeah. So these are total number of walks of length less than or equal to n minus 1, right? You remember that Rajesh sir, while proving bipartite graphs, okay? So he used this, right? Of course, he used that, yeah, okay, yeah. So he used only diagonal part, I think, right? Yeah, so you are aware of this. So what I want to say that if it is a connected graph, then I plus a square and so on, a power n minus 1, that is a positive. Every entry in that is positive. Okay, then automatically that is irreducible also, right? Every positive matrix is irreducible. Okay. So am I clear about or any questions here? Please, can you take yes, please? Are you okay? Yeah. So and you understand that computing a square, a power n minus 1 may not be tough. Okay, so this is one algorithm. I'm not saying this is the only, but okay, this is only one direction. What about the converse? Right?
A to the power n minus, if we had that time was a positive income instead
Yeah,
of getting I.
yeah, yeah. So because see, one, I some so for example, this is already greater than or equal to. Here, you know, greater than or equal to means entry wise greater than or equal to, right? Yeah, yeah. So I plus a power n minus 1 automatically greater than or equal to this, so it is positive. Yeah. Sorry, that is what you are saying, please. Sorry.
Sir, I